Hi everyone, I am Mazhar. Today I will present our paper CHIMERA, Autonomous Planning and Orchestration for Malware Deception. It's a joint project between University of North Carolina at Charlotte and Carnegie Mellon University. The project was funded by Office of Naval Research and Army Research Office. The motivation of our work is that existing prevention and detection-based defense are not effective against malware. For example, the recent data breach report shows that hundreds of terabytes of highly sensitive information have been lost for more than 150 organizations in 2021. The FBI reported that more than $13 billion has been lost due to cybercrimes in terms of spear phishing attack, account takeover, ransomware, and information stealer. Every 2 seconds in the US, people are losing their sensitive data because of information stealing malware. Every minute, almost 6 successful malware attacks happens. Recall that the May 2021 ransomware attack in Colonial Pipeline cost them millions of dollars. Therefore, we have to think about alternative solutions, such as cyber deception, which is a promising defense technique against APT actors. The limitation of current deception mechanism is that they mostly provide static configurations such as virtual machine or a sandbox that are standalone from the real machine, which can easily detected by the APT actors. They provide lack of automation, which makes them more complex and expensive to use. They have single point of failure, and most of the time they provide monostage deception, which means the deception environment can only protect a single phase in the whole APT lifecycle. Therefore, to address all of this challenge, an adaptive and dynamic deception is required that can create and orchestrate honey resources embedded in the operational environment at real time. Cyber deception is an intentional misrepresentation of the system's ground truth so that we can manipulate and confuse adversaries' action. Adversary may still execute their attack actions, but of course under the rule of the defender, so that the defender can achieve the following 4 deception goals. The first one is divert, which means that although the adversary may launch their attack into the real system, but still we can divert them into false or honey goals. We can distort their view so that they get confused while executing their attack action. We can deplete the adversary so that the attack propagation gets delayed. And then finally we can discover new attack techniques which can be used to protect against this type of APT actors in future. Because of the effectiveness of cyber deception, it is getting more and more popular, and we expect that the global market of cyber deception technology will grow up to $2.3 billion by 2022. The problem that we solved in this paper is that given the cyber resource that we wanted to protect against the malware, the malicious process such as information stealer or ransomware, the attack specification in terms of attack techniques or attack action, and their corresponding deception action, our goal is to develop a deception environment that can generate an optimal deception planning, autonomous creation and orchestration of the deception actions, so that we can deceive the malware to achieve the 4D deception goals. To develop such framework, we have to solve the following research challenge. First, we have to create a model that can consider both the attacker's behavior and the deception behavior simultaneously. We have to provide an optimal deception plan considering the uncertainty in the attacker's behavior, which can induce high space and computational complexity. Adaptive and dynamic real-time deception that can cope up with adversaries who may change their attack plan as well. And embedded deception, which can be integrated in the operational environment without breaking the system's integrity. To achieve that, we developed CHIMERA that provides the following deception capabilities. It creates a new attack propagation graph called deception graph to model the dependency between the attacker's action and the defender's action. We provide an API to MITRE attack mapping. We optimize the goal-oriented deception decision-making and provide the autonomous orchestration of deception actions. And finally provide API-level hooking that enables the embedded deception environment. Before go deep into our framework, I will first describe how APT actors work. They usually follow the TTP kill chain shown in this figure. The TTP means techniques, and procedures. The tactics are the adversary's objective. For instance, the adversary will look for sensitive resources, which is called the discovery. So discovery is a tactic. The techniques are how adversary achieve those goals. For instance, the file and directory discovery is a technique to achieve the discovery goal. The procedure are the specific approach or implementation to achieve such techniques. For example, the shell command dir or ls can be used to discover file and directory. This table shows the mapping between the system API to attack technique. The reason for this mapping is that from a system, what we can get is the sequence of API calling by the malware. But to understand the high-level context, we have to map those API calls to attack technique so that we can predict the next move of the adversary. For example, the attack technique file and directory discovery can be mapped with the API calls such as create current directory, create file, read file, and so on. We give this a name called list directory as an attack action and redirect to honey directory as a defense action against this attack action list directory. This is the overview of our framework. First, we collect attack techniques of known APT actors from different sources such as MITRE ATT&CK, malware analysis tool like AnyRun or hybrid analysis, and so on. Using those techniques, we create a deception graph. The deception graph generation unit needs specifications like type of attacks, states, transitions, and more. Using the deception graph, an optimal deception policy is generated. Now, in the production machine, when the malware executes its attack action, the API hooking agents alerts the malicious activity to the API monitoring tool. The deception agents gets the alert as an observation. Using the policy, the deception agent deploys an optimal deception action into the system. The hooking agent then delegates the malware's API call to the honey factory and returns decoy responses back to the malware. Now let's get details about the deception graph. The deception graph into our framework describes the attacker's current position using the kill chain techniques, which considers whether the deception action is successful or not. It models the interaction between the attacker and defender using attack states, which means that the attacker is successful, or the deception states where the defender is successful. Here is an example deception graph of information staying malware. The white states represents the attack state or real state, and the gray state represents the deception state or the honey state. All of those white states are different types of attack techniques. For example, when the adversary executes a malware, it is in the user execution malicious file state. Now, if the defender does nothing and the attacker executes list directory to discover the file and directories, it will reach to the file and directory discovery state. But if the defender predicts the attacker's action and takes an appropriate deception action such as redirect to honey directory, then instead of going to the file and directory discovery, it will go to the honey file and directory discovery states. To generate optimal deception planning, we have to consider the following key criteria. First, the deception planner must use a stochastic model because of the unknown state of the system due to partial observability, which means that we have imperfect observability of the attacker's current position, and the dynamic behavior of the adversary, which means that we do not know the true strategy of the adversary. Therefore, we formulate the deception planning problem using partially observable Markov decision processes. We predict the adversary's behavior from previous observation. The state transition of our POMDB model depends on the historical adversary behavior and the deception action effectiveness. Our POMDB model considers the following parameters. S is the finite set of state space, which consists of attack states and deception states. A is the finite set of deception actions. T is the transition functions. Omega is the finite set of observation, which is similar to the state space in this problem. R is the reward function. And gamma is the discount factor, which indicates that how far in the future we'll consider the consequence of the current deception actions. Here's an example how our decision-making process works. The deception planning agent has two modules. One is the belief updater and another one is the deception action executor. It may take some predefined parameters such as discount factor, cost of deception actions, and so on. Now let's say that the initial belief is that the attacker is about to stage the data. So the belief updater calculates a new belief saying that sensitive file and directory will be discovered. Therefore, the action executor executes a deception actions which is put decoy files into the directory. From the system, we observe that the sensitive data is still staged, which means that our deception actions may fail. Now the update belief will be higher probability for sensitive data is staged. Thus, the action executor will execute a new deception action which is replace sensitive file with honey files. Now from the system, we get an updated observation which is honey data is exfiltrated. That means that our deception action is successful. Now let's see how we calculate the state transition. The state transition specifies the probability of transiting from current state to next state for a given defense action. In our case, we calculate the probability of state transition based on two factors. One is the system behavior, and another one is the likelihood that adversary will take certain attack action given a specific state. The value of the system behavior is defined either 1 if it is valid or 0 otherwise. We call a system behavior is valid if a certain deception action is compatible against an attack action and it leads the adversary to reach from current state to a deception state S prime. Now for each state transition, we calculate the reward for the defense action. The reward depends on the following parameters. The first one is the QS prime, which indicates the risk. If a defense action is failed, then there is a chance that the adversary may steal the information, which associates a risk. The second parameter is the WI, which is the incentive if the defense action is successful. It is multiplied with ZI, which indicates that certain deception action can achieve one of the 4D deception goals like diversion, distortion, depletion, and discovery. The final parameter CD is the installment cost of the defense actions. Due to time constraints, I will not go over the details of the rest of our modeling parameters and their equations, but I will highly encourage interested people to read our paper for better understanding. To evaluate our framework, we consider the following criteria. The first one is the effectiveness of our deception, then the quality of our deception, the optimal deception policy generation, and the system overhead due to deception action deployment and their dynamic orchestration. Here is the dataset that we use to evaluate our framework. We get more than 4,500 malware from different families like information stealer, ransomware, and remote access trojan from VirusTotal and Malware Share. We calculate the deception efficiency by running different malware samples into our framework. We observed that 95.93% of malware took our bait and ran to completion. For 3.18% of malware, we deceived them, but we cannot say that they took our bait or not, as they send encrypted traffic to command and control server. We cannot deceive 0.89% of malware samples because they fail to run in the production environment due to not complying with the system requirements or they are obfuscated. CHIMERA can deceive malware to discover TTPs. Therefore, we compare the power of CHIMERA's dynamic analysis capability with existing malware analysis tools such as Cuckoo Sandbox and AnyRun in terms of TTP discovery. We showed that CHIMERA outperforms in discovering new TTPs compared to existing tools. For example, both AnyRun and Cuckoo missed the file and directory discovery technique of Lokibot, while Lokibot uses dir shell command procedure to discover the profiles.ini file for Mozilla Firefox web browser. To calculate how optimal CHIMERA generated policy is, we created a static deception planning using SMT. Then we run 2 RAT samples using both static planning and CHIMERA planning. We show that the static planning is capable of engaging with the naive basic RAT for around 10 minutes on an average before the basic RAT client quits. However, advanced PUPI write client detects the deception environment because of static planning in a minute. But in both cases, CHIMERA deception planning was able to engage with the attacker for more than an hour. Similarly, we compare the data exfiltration probability as well. We take a sample of information stealer, Lokibot, and run into both static planning and CHIMERA generated planning environment. We saw that in static planning, the data exfiltration probability is almost 1. But for CHIMERA planning, the data exfiltration probability is nearly 0. We measure the overhead in 2 different ways. One is the policy generation overhead, which is offline, and another one is the optimal action recommendation in real time, which is online. We created 3 deception graphs for information stealer, ransomware, and RAT, each having different number of states. We show that the maximum policy generation overhead is around 600 seconds for information stealer that have 37 number of states. But the maximum delay to recommend a deception action is 15 seconds, which happens in the production environment in real time. In conclusion, we introduced a new framework called CHIMERA that provides an optimal deception planning to deceive APT actors and achieve different types of deception goals. We use partially observable Markov decision processes to obtain the optimal deception action planning. We developed the deception environment using Windows API hooking. We evaluated CHIMERA with more than 4,500 malware samples from 3 different families. We deceived those malware samples with high efficiency, around 95.93%. The one important limitation of our framework is that malware that can bypass API hooking cannot be deceived by CHIMERA. Thank you.